Welcome to Paradise Podcast number 79, and today we're looking at the effects of wall temperature on flying wing aerodynamics. So before we talk about this, let's look at what a flying wing is. So if you're listening to this on Spotify or whatever podcast player you're listening on, know that we also have the video on YouTube. So you can go to YouTube and just look at it there. But I'll describe it to you anyway. So if you know what a B-2 bomber looks like it's the quintessential stealth air fighter or aircraft that you see in movies. For example, in Captain America, the first one, when he's going down over the Arctic, whatever it was, I think that was also a flying wing. It's just a slender profile. It looks almost like a boomerang, but just flying like with the point forward. So those are flying wings, and the reason why these are cool aircraft are because first of all, they don't have any tail, so they don't have any of the horizontal part or the vertical part, and everything is controlled just by the one wing. And we're going to look at the effects of the wall temperature on the aerodynamics of the, the airfoil because the wall temperature does make a difference. And this falls into a category called active flow control. So flow control is what it sounds like when you're trying to control the flow. And active means that you're changing the system in an active fashion to change the flow even more. So passive flow control is good from the point of view that it's usually more simplistic than active flow control devices. So it means that you don't need to have power. It's just geometry based. So if you have your geometry, it's always going to perform the same way, or at least within a very narrow window of operation. Whereas active flow control devices, they are usually much more delicate and they also require power, but you can use them in far greater range of situations. So that means that you can get a much better efficiency and a much better situation out of them. So the trade-offs, and changing the wall temperature typically comes under the active flow control umbrella. So to look at the effects of the wall temperature on flying wing aerodynamics, we're going to look at a paper called Numerical Study on the Influence of Wall Temperature Gradient on Aerodynamic Characteristics of Low Aspect Ratio Flying Wing Configurations. And this is open access, so you can find it in the link in the description. So let's talk about low aspect ratios first. So if you have a regular wing, like if we've all flown an airplane and you look at the wing, it's quite long, but it's quite narrow. So the ratio of how long that wing is to the like width of it is the aspect ratio. And the greater this number, the longer the wing is compared to that the width of it. So with low aspect ratios, it means that it's quite short and stubby. And we'll get into some of why this is important in this podcast. So let's continue now. So the flying wing configuration eliminates the vertical and horizontal tails compared to conventional configurations, which improves the aerodynamic efficiency and has excellent stealth capabilities and structural performance. So why does it have better aerodynamic efficiency? The main reason why is because you don't have the fuselage or the tail section. So these parts, even though they are good in terms of, you can generate extra lift with them depending on how you configure them. And also, it's easier to control the aircraft with these surfaces, including even the fuselage if you design it properly. They are usually far less aerodynamic efficient than just having a regular wing. So in other words, you're going to have much greater drag compared to how much lift that you want to produce. The flying wings are much better than that way. And also they say that it has excellent stealth capabilities. So why does a flying wing without a tail section or anything like that have better stealth capabilities than a regular aircraft? The reason why is because the more minimalistic you can make it, the less there is for radar to bounce off of surfaces. The less surface you have to bounce radar off, the more undetectable it is. And it's also harder to see because it's more two-dimensional than three-dimensional. So when you change the angle of attack or whatever, you can make the aircraft almost pretty much invisible to the naked eye. Under certain conditions. And it's really cool. So they say, however, the lack of stabilizers and control efficiency has long limited the development of flying configurations. So that's the downside, or those are the downsides. With the development of modern technology and the emergence of new design concepts, the defects of flying wing configurations can be effectively restrained within a certain range, which gradually increases the practicality of the flying wing configuration. The American B-2 long-range bomber is a successful application of high aspect ratio flying wing configurations, as I showed the picture before. It looks like just a regular wing just flying around. So this is interesting. The shock wave drag in transonic and supersonic regions can be reduced by decreasing the aspect ratio and increasing the leading edge sweep angle. So we talked about the aspect ratio to begin with and why that is important in terms from a geometric point of view. Let's talk about the aerodynamics of different aspect ratios. So in figure 1, we have the flying wing with different aspect ratios, and just means that they're either like much wider, much broader, or much stubbier. If they're much broader, it means that they usually have a higher aspect ratio. And as we mentioned, that is, they say that the wave drag, so wave drag is the drag that occurs due to shock waves, which means that when you get close to the speed of sound, you start compressing the flow so much that it can't really go anywhere. And it just creates this really massive pressure in front of the aircraft or at certain points in the aircraft's geometry that increases the drag. But this drag, which is very large at high subsonic speeds, can be reduced by decreasing the aspect ratio. So by making them stubbier, you can reduce the shock wave, or the shock drag, sorry, and also by increasing the leading edge sweep angle. So the sweep angle is how much those leading edges are tapered, so like how much they're like pulled down and like backwards, and the greater the angle, the more sweep angle that you have, and that's beneficial for reducing the drag. Why that is, it has to do with, I'm not going to go too much into this, but it has to do with the airfoil profile, and when you sweep the wing, that changes that a little bit, and that changes the critical Mach number, which I'll talk about a bit later. I've also covered that in other podcasts. But anyway, let's move on. So at present, the cruise speed of such low aspect ratio aircraft is in the high subsonic speed range, and the research on drag reduction is of great significance to the design of the entire aircraft. Because of its high lifted drag ratio, the high aspect ratio flying wing is used in transport aircraft, has been used in transport aircraft for a long time, but its drag divergence Mach number is small, so it is not suitable for high subsonic flight. So there's a lot in that. Let's talk about this. Because of its high lift to drag ratio, so that means that it's producing a lot of lift compared to how much drag that it's producing, which is good usually, particularly for aircraft. The high aspect ratio flying wing, so that means that it is very broad, is used in transport aircraft for quite a long time, but its drag divergence Mach number is small. So the drag divergence Mach number, also known as the critical Mach number, which I mentioned earlier, is the free stream velocity at which the flow over the aircraft will start to become sonic at some point. So it will be the point where you start crossing the sound barrier. So this is called the critical Mach number. So for some people, like me included, when I first heard about the critical Mach number, I found it strange that you could have like the flow over the aircraft would be sonic when the free stream velocity isn't sonic. But then I had to think about it and thought, okay, it makes sense. And the reason why is because the flow over an object, not just the aircraft, not just an airfoil, but any object, will typically accelerate as you go over certain regions. So if you had a free stream velocity of 0.95 Mach number, let's say, you might accelerate the flow to the point where it's now 1. So you're at the sound barrier. So that's the critical Mach number. So the free stream velocity is 0.95. That's the point at which you'll get supersonic flow or sonic flow over your object. And because of it has a very low Mach number, critical Mach number, the high aspect ratio flying wings, they're not good for high subsonic flight, because it means that once you start getting to, let's say, Mach 0.9 or 0.85, you're going to be getting sonic flow over the flying wing, which increases the drag. Whereas if you have low aspect ratio wings, you can go higher. You can probably go to 0.95 perhaps and still get a lower drag, because you're not getting as much sonic flow over your wing, or even none at all. So that's a benefit of that. They also say because of its large leading edge sweep angle, the low aspect ratio flying wings can fly in high subsonic speeds and have high endurance efficiencies. So these are alternative layouts for future fighters. The friction drag on the aircraft surface can be significantly reduced by delaying the boundary layer transition on the aircraft surface and maintaining the laminar flow as large as possible. So in other words, making the flow over the aircraft as laminar as possible for as long as possible. They're going to term this natural laminar flow. And the reason why I point this out is because we're going to be covering this in the next few minutes. In the design, the factors affecting the aircraft surface flow state mainly include the pressure gradient in the flow direction, the surface heat flow, and surface mass transfer. So in other words, the pressure gradient in the direction that the flow is going, and the temperature of the surface, and also the mass transfer within the boundary layer affects the aircraft's flow. These factors have significant effect on the stability of the leading edge laminar flow and are the possible sources of disturbances, especially for aircraft flying with low turbulence. So in other words, this is quite an interesting fact. I remember bringing this up when I was first doing research into aircraft, like quite a lot of years ago, more than I care to remember. And I remember talking to my supervisor. I said, we're talking about Reynolds numbers and what Reynolds numbers are required to get turbulent flow over aircraft. And I said to him, well, this is an interesting fact when you go up 30,000 feet, because there are very few disturbances up there. The flow over a 747, for example, is laminar to a certain extent. Whereas if you were to, even though like the Reynolds number is like 10 million or more, whereas if you were to come down at sea level and have a 10 million Reynolds number, you can always be certain that the flow over any streamline object will be turbulent. The reason why is because up 30,000 feet, you have very few disturbances. Down at sea level, we have a lot more disturbances. There's a lot more around creating these disturbances. So why are disturbances important for Reynolds numbers? The reason is because, and the laminar and turbulent boundary layers, the reason is because the disturbances create turbulence. So if you have a big enough disturbance, that will then break down in 3 dimensions and create a turbulent flow. If you have a very small disturbance, it means that the viscous effects of the flow will dampen that out and you won't get transition to turbulence. So that's why they're talking about this here in terms of how these different factors can contribute greatly and influence the boundary layer transition point in these flows where there are very low turbulence levels. So let's move on now. When the wing sweep angle is less than 15 to 20 degrees, downsteady flow direction is the leading cause of the transition from laminar to turbulent. However, the decrease of aspect ratio means that the leading edge of the aircraft has a large sweep angle. So 3-dimensional instability mechanisms are dominant, such as secondary flow and cross-flow instabilities. So what does this mean? These are potential ways that a laminar boundary layer can break down into a turbulent boundary layer. So there are many different ways that this can happen. The quintessential ones that you'll learn, like in any textbook, is Tolman slitting waves, which are like when you have these disturbances and they create these little waves and then they break down 3-dimensionally, as I mentioned. But then there are other situations, such as the secondary flows and cross-flow instability. So when you have a flow moving at an angle to the rest of the flow, that then creates these roll-ups and they'll break down, and that can create turbulence as well. So when you have reduced aspect ratios and higher, larger sweep angles, you're then running the risk of introducing these problems and then triggering turbulent boundary layers at a lower Reynolds number. So in this case, the natural laminar flow cannot be realized unless active flow control methods are combined. So in other words, let's heat the wall, which they're going to look into in this way, in this paper. The influence of the wall temperature gradient on laminar flow stability and boundary layer transition is one of the hotspots in aerodynamic research. As early as the 1947, Lees, a researcher, I guess, found that the wall cooling can stabilize the 2-dimensional disturbance in the model boundary layer. So it's interesting. The temperature of the wall can affect the boundary layer transition point. In 1976, another researcher found that wall cooling can stabilize the 2- and 3-dimensional disturbances in transonic flow. So that's another step forward. In 1980, another researcher summarized the experiments on wall cooling at hypersonic speed and found that in most cases, the transition Reynolds number increases as the wall temperature decreases. So let's talk about quickly hypersonic speeds. It's one definition that isn't often covered. So we know subsonic speeds, supersonic speeds, and now there's hypersonic speeds. What's the difference? So subsonic and supersonic are quite obvious. It's when you go from being slower than the speed of sound to faster than the speed of sound. But hypersonic speeds, that's when you go so fast that the gas that you're in terms of the Earth, our atmosphere, air, starts to change its composition effectively, where you start to strip electrons off of the molecule, off of the atoms, and make them plasma. And that happens when you go so fast that there's a lot of heating going on. So that's the general distinction between supersonic and hypersonic flows. In supersonic flows, you don't really get that plasma forming. In hypersonic flows, you do. And the general Mach number that this happens is around a Mach number of 3, but depending on where you find it, it can range from 3 to 5. That's the general range that people quote, but that's the difference there. So let's move on now. Research on the influence of wall temperature on the large sweep angle and three-dimensional flows started relatively late. In 1986, a researcher carried out a numerical study on wall heating on a slender symmetrical blunt body similar to a fuselage and found that heating can reduce friction and total drags. So the drag in total is made up of different components. We mentioned earlier the wave drag that occurs when you go very fast, but there's also something called friction drag. There's also something called pressure drag, and there's also something called induced drag, which reminds me now, I should probably mention that we were talking about high aspect ratio wings before and why they were very efficient in terms of lift to drag ratio. I did mean to talk about the induced drag there, but I forgot. So let's cover this quickly now. So I mentioned that high aspect ratio wings, they have a much greater lift to drag ratio, which means that they're more efficient than low aspect ratio wings. One of the main reasons for that is the reduction of something called the induced drag. The induced drag is very well known in terms of its visual representation, which is the vortices that it produces at the wing tips. If you go to Google or DuckDuckGo or whatever, and you type in just wingtip vortex, you'll see a bunch of really cool pictures showing this. And what happens is the high pressure on the one side of the wing, well, like one surface, bleeds over to the low pressure on the other side, and this creates a vortex. This is the visualization of induced drag, and induced drag is what it sounds like. It's drag. It's a loss. So low aspect ratio wings have a lot greater induced drag than high aspect ratio wings because near the wing tip, you're producing a lot more lift than a high aspect ratio wings, relatively speaking. And then that results in a much greater pressure difference, and that creates a greater vortex, a stronger vortex. So by having a high aspect ratio wing, you can reduce reduce the induced drag by reducing the strength of the vortex and the amount of flow that's bleeding over. So that's why high aspect ratio wings have a better lift to drag ratio than low aspect ratio wings. So sorry, I didn't mention that before. It slipped my mind, but now we've all caught up. So let's move on. On this basis, which is that for heating of slender symmetrical blunt bodies similar to fuselages can reduce friction and total drags when you heat them. On this basis, another researcher carried out an experimental study of heating control on different positions of slender blunt bodies in 1999 and found that the more forward the heating position, the larger the heating area and the greater the drag reduction. So that makes sense. When you move it forward, you're affecting the flow further upstream, which means that it can't develop to the point where you can't control it anymore. And this is often the case for flow control devices on wings. The further upstream you can go, usually the better. So a couple of researchers believed that the change of drag was due to the influence of wall temperature on the turbulent boundary layer, but did not point out the mechanism. Subsequently, numerous research and numerous works on this area have emerged, but mainly focused on the hypersonic field or the development of certain disturbances in the boundary layer with a small sweep angle. Therefore, the effect of the temperature gradient on flying wing configurations with small aspect ratios concerning the boundary layer transitions need more exploration. That's what this study is looking into. They're looking at the effect of the surface temperature gradients on the flying wings aerodynamics, particularly when they have a large sweep angles and small aspect ratios. So they're going to look at the variations of the wall friction coefficient, transition Reynolds numbers, and the turbulent boundary layer flows with wall temperatures. And they said that it's emphatically investigated. So I'm quite excited about that. Anything emphatically investigated, I'm up for. So let's move on to the results now. They looked at CFD, but I'm not going to cover that because we've covered it previously in other podcasts, just general CFD stuff. If you like, you can look at the paper and go through their CFD here. Let's move on to the results here instead. So let's look at the influence of the temperature gradient on aerodynamic characteristics. They have, first of all, let's find it here. Figure 7, in comparison of the lift and drag coefficients at different angles of attack, and they compared their CFD to experiments, so validation. And they line up quite well. The drag is a little bit under predicted at low angles of attack, but it's still quite close. It's within a few percent. The lift coefficient is very nice. Like it lines up very well. So good job on that. And the Mach number is 0.9, so it's very close to sonic. In fact, I wouldn't be surprised if they had sonic flow over some parts of their wing. Okay, so let's move on to figure 8, which has the influence of the temperature gradient on the model drag coefficients. So here is a really cool graph because it breaks down the drag in terms of its components from the total drag. Now we have the pressure drag and the viscous drag. And the viscous drag is just another word for the friction drag. So when you, and I should mention that on the x-axis, they have a normalized temperature. So this shows you the difference between the free stream velocity and the wall. And when it's 1, it means that they're the exact same temperature. When it's not 1, it means that there's a difference in temperature, and that means you're going to have a heat transfer occur. You can't have heat transfer between two objects that are the same temperature because heat only transfers from hot to cold. So when it's 1, it means that they're the same temperature. Now, interestingly, the total drag will always reduce as you increase the temperature of the wall. And that is because the friction drag decreases as well. Interestingly, though, the pressure drag increases slightly when you increase the wall up to the wall temperature, sorry, up to a certain point, and then it starts to reduce slightly. However, these changes are very minor, and because we have an airfoil in at longest attack 2 degrees, the flow is almost completely attached. There's almost no wake in this situation, and the pressure drag plays a very minor role in terms of the total drag. So to give you an idea, the total drag at when the temperature of the wall is the same as the free stream is what's that, 0.0072. The pressure drag makes up about 25% of that, and the friction drag makes up the other 75% of that. So the friction drag makes up a far greater proportion because the friction at this point is the dominant contributor to the total drag, which means that when you have a reduction in friction, which we're seeing here with increased wall temperature, that's going to play a much greater role in the reduction in the total drag compared to the pressure drag. So the increases in the pressure drag are minimal in the grand scheme of things. They say that figure 8 shows the model drag coefficient variation with the model surface temperature gradients. Here, the pressure drag coefficient and viscous drag coefficients are shown. When the wall temperature increases from the adiabatic temperature from 291 Kelvin to 500 Kelvin, the friction drag decreases by approximately 9.6% and shows good drag reduction effect. Now, that's not a huge amount when you think about it. When you go from a temperature of 291 Kelvin to 500 Kelvin, so almost like it's like 70% increase, you only get a 9.6% reduction in the friction drag coefficient. So that's not a huge amount, but it's better than poking the eye. So figure 8, the wall temperature gradient has an opposite effect on the friction and differential pressure drags. The specific performance is that with the increase of wall temperature, the viscous drag gradually decreases while the differential pressure drag slowly increases with a small amplitude. So that's what I mentioned earlier, just in different words. So moving on to figure 9 now, which shows the influence of the wall temperature gradient on the model lift and the pitching moment coefficients at an angle attack of 2 degrees and a Mach number of 0.9. They say figure 9 shows the influence of the wall temperature gradient on the lift and pitching coefficients of the entire aircraft. With the increase of wall temperature, the lift and pitching moments varied linearly, approximately linearly. When you increase the temperature gradient, the lift coefficient decreased linearly, but the moment coefficient increased linearly, the opposite directions. According to equation 2, the temperature difference between the underflow and the turbulent flow regions is about 1.8 degrees Kelvin under adiabatic conditions. However, when the wall temperature is close to the static temperature of the incoming flow, its aerodynamic characteristics are basically consistent with the results of an adiabatic wall. So an adiabatic wall means that there's no heat transfer to or from it, which means that it's the same temperature as the free stream velocity, effectively. Therefore, when the wall temperature is close to the static temperature of oncoming flow, the wall heat transfer exerts a small aerodynamic influence. So in other words, as we suspected, when the heat transfer is minimal, you can't expect too much of an effect on the lift or pitching moment coefficients. That's because there's no real active flow control going on. You're not really changing anything. So that makes sense. So let's move on to figure 10, which covers the influence of the temperature gradient on flow characteristics of the model surface. So figure 10 shows the friction coefficient distributions on the upper surface of the flying wing model with the wall temperature, with different wall temperatures at a Mach number of 0.9 and an angle of attack of 2 degrees. And it shows for an adiabatic wall, so in other words, no change in, no heat transfer. Then we have a like very cool wall compared to the oncoming flow, and then a very hot wall, and then everything in between. Now, they say about this, the influence of the temperature gradient on the surface flow characteristics is mainly reflected in the location of the boundary layer transition and friction drag in the turbulent boundary layers. Figures 10 and 11 show the contours of the friction stress coefficient distribution on the upper and lower surfaces for different temperature gradients. Under various wall temperature gradients, the laminar flow areas of the leading edge of the model are small because the model has a large sweep angle of 65 degrees. So let's talk about this in English. So figure 10 shows 7 different configurations, one where the wall is the same temperature as the oncoming flow, and then from then on, they are different. And it has the friction coefficient plotted in color, which is quite nice. And in all of these figures, you see a very distinct line where the friction coefficient goes from being very low to being very high. And this indicates where the transition is occurring. I believe that's where it is. And I don't see anything pointing to the contrary. If you know anything other than that, let me know in the comments below, but I'm quite certain that's what it's indicating here. And it makes sense. And what they're showing is when the wall heating is very, when it's cooling a lot, the friction coefficient is very large after this point compared to when the wall is heating it up. And also the trailing edge, there's a bit of a change in the friction coefficient right at the back of the wing. So that's quite interesting. They say on the adiabatic wall, the laminar flow range of the upper wings decreases at low wall temperature. The hot wall is the opposite to the cold wall. Okay, I know that. The transition regime moves backwards and the laminar flow range increases. So in other words, when you have a hotter wall, it delays the transition to turbulent. While the lower surface of the airfoil, let's move to that figure now, figure 11, it has the exact same idea plotted. It has the friction coefficient plotted on the lower surface for different temperature differences at a Mach number of 0.9 and an angle of attack of 2 degrees. Sorry. They say while the lower surface of the airfoil is under the influence of the forward pressure gradient, which is similar to that of the upper airfoil due to the wall temperature gradient and the effect of the laminar flow range is more obvious. The temperature gradient not only affects the transition behavior of the laminar boundary layer, but also affects the friction coefficient in the turbulent region. So that's interesting. It not only affects where the transition occurs, it also affects the friction coefficient after you've transitioned, which makes sense to some extent. The energy of the flow is still being affected by the wall temperature. It's just that we often don't think about the effects of the wall temperature after transition, because we often just want to know where the transition point is and how that is affected by the wall, and the wall temperature at least. They say the temperature gradient not only affects sorry, I covered that as well. The turbulent flow after transition in the case of the cold wall has a larger friction drag coefficient and smaller friction drag in the case of the hot wall. So in other words, the hot wall seems to be much better for reducing drag overall, for a wing at least. I'll get into later why I think it's only just for a wing or a streamlined body. Let's move on now. So figure 13, they have the influence of the temperature gradient on the turbulent boundary layer characteristics. And they have the evolution. Figure 13 shows the evolution of the friction coefficient at a wing section of fairly inboard and a Mach number of 0.9 and an angle of attack of 2 degrees. And they have this at 3 different wall temperatures, one where it's significantly lower, so it's 0.344, one where it's the same, and one where it's much higher, 1.782. And they have the upper and lower surfaces plotted, the friction coefficients, as you go along the chord of the wing, so from upstream to downstream. They say in the laminar flow region, the friction coefficient is not significantly affected by the wall temperature gradient, but clearly decreases as the wall temperature increases after transition. So that makes sense if you look at all these points. First of all, we can see that the point at which the flow transitions is significantly closer to the leading edge when the wall is cooler. As you increase the wall's temperature, this transition point moves back very drastically. Also, when you have a cold wall, for example, the point at which the flow transitions, the friction coefficient is 0.0055 about, both for upper and lower um, surfaces. But when you have the temperature very high, so it's 1.782 times the regular friction velocity, approximately, the friction coefficient is now only about half that, so it's much lower, and it continually decreases. Now, in figure 14, they have the laminar boundary layer profiles at different wall heatings. And this is interesting because it shows you how the velocity of the flow near the wall is, and this directly relates to the friction drag. So they say the influence of the temperature gradient on the boundary layer is analyzed using the boundary layer thickness and the outflow velocity at the entrance wall. Compared with the laminar boundary layer, the turbulent boundary layer has a greater velocity profile, and figure 14 shows the velocity profile. So let's talk about this. So these boundary layer profiles show you how what the velocity of the flow is as you get further away from the wall. The higher you go, the more this velocity is, which makes sense. And it's normalized to the free stream velocity effectively. And when you have a very cool wall, so the black line, this is the quintessential laminar boundary layer profile, and it's very nicely curved, and it's fairly gentle in terms of its gradient, but not nearly as gentle as when you increase the wall temperature. So when you increase the wall temperature, interestingly, these velocity profiles become very like the gradient isn't nearly as sharp in terms of how quickly the velocity is increasing as you go higher up into the flow. And that means that the velocity near the wall is much lower, which means that you're going to have less friction, which means you have less friction drag. And that all sums up very nicely. It shows you how, so far we've seen how the friction drag behaves as we increase the temperature of the wall, and now we know why it changes like how it does. It's because the velocity of the flow very close to the wall is much lower, and that's quite nice. So then we have the turbulent boundary layer profile. That was laminar boundary layer profiles, by the way. So that's before transition. We have the turbulent boundary layer profiles as well. Interestingly, these aren't affected nearly as much when you change the wall temperature. However, it seems to be enough just to change the friction drag a little bit, as we mentioned earlier, as you increase the wall temperature. That still reduces the friction drag a little bit in the turbulent regime. It just, its main effect is in the laminar part where it delays transition, and that is beneficial for the friction drag. Now, interestingly, in figure 16 shows the change of the model's transition Reynolds number at different temperatures. So where the transition will occur in terms of Reynolds number based on the wall temperature. The wall heating increases the transition Reynolds number and delays the transition. So in other words, when the control temperature increases from 292 degrees Kelvin to 500 degrees Kelvin, the transition Reynolds number increases by approximately 28%. So that means that you have to have a 28% higher Reynolds number just to get the same flow, to get the transition occurring. So that's how the wall temperature is positively affecting the transition point. And interestingly, it's somewhat linear. So in other words, when you have the wall temperature was 0.382, I believe. What was that here? It's 0.344, and you put it to 1. The change there is approximately the same as when you move it a bit higher to 1.782, and it has a fairly linear trend to that. So they have a new parameter now called eta, and it's defined in equation 6. I'm not going to go through equation 6, so I'll let you just see that equation there, but I'll just explain what it means. So the heating causes a temperature gradient in the boundary layer with high temperature near the wall and low temperature away from the wall. This result further leads to viscous stratification with higher air viscosity coefficient and density stratification with lower density near the wall in the boundary layer. And eta is a measure of that. So they have, let me zoom out here so you can see, they have figure 17, shows the distribution laws of the Reynolds number shear stress and the turbulent kinetic energy of the boundary layer. And in A, there's the Reynolds shear stress, and B, they have the turbulent kinetic energy for different etas. And they say that The high wall temperature reduces the Reynolds shear stress and thermal kinetic energy in the boundary layer. That is, the hot wall suppresses the tangential and positive pulsations and stabilizes the flow. So in other words, the disturbances that you'll see that often create transition, the increase in the temperature of the wall suppresses these features, or suppresses their effects, I should say. Therefore, the wall heating control delays the transition from laminar to turbulent flows, increases the transition Reynolds number, and enlarges the laminar flow regime. So, in conclusion to this paper, the high wall temperature can increase the transition Reynolds number mainly because the high temperature model surface can increase the viscosity coefficient of the fluid in the laminar boundary layer, thus increasing the viscous effect and reducing the Reynolds number stress and thermokinetic energy, as well as restraining the pulsation and increasing the flow stability. Let me just talk about this and break that down because there's a lot in that. So they're saying the high wall temperature means that the viscous effects increase. So why is that important? That is important because when you look at the Reynolds number, as I've covered it a lot of times in other podcasts and in the courses that we do, the Reynolds number is effectively a measure of the inertial effects of the fluid to the viscous effects. When you look at the equation, on the top line, you have the inertial effects, so how much the flow wants to keep doing what it's doing. On the bottom line, you have the viscous effects, which is how much resistive force there is to the flow doing what it wants to do. So if you increase the viscous effects, that's going to damp out the inertial effects. Now, when it comes to transition, the inertial effects are what really drive transition. So when you have a disturbance, when it has high inertia, it means that it wants to keep doing that and it's going to keep propagating through the system. If you can increase the viscosity, it will then sap away that energy and it will dampen it, and it means that it can't propagate through the system, which means that transition cannot occur. It will stay laminar, it will die out. So that's what this really means here. The second conclusion is that the heated wall reduces the velocity gradient in the bottom of the turbulent region of the model and the viscous shear stress near the wall, thus reducing the friction stress and coefficient at the wall. Wall heating can delay boundary layer transition, enlarge laminar flow areas, and reduce friction drag in the turbulent flow area, thus reducing the model drag. The higher the wall temperature, the smaller the model drag. Now, I was going to talk about why I think that these results are really just limited to streamlined bodies, and I think I should talk about that here. So, as I mentioned, I think that these conclusions here, we were looking at an airfoil at 2 degrees angle attack. Now, at 2 degrees angle attack, the flow is pretty much completely attached to the wing. There's almost no wake. And if you push the wing to high angles of attack, you're going to start getting a much greater wake, and the flow is going to start to detach. It's going to stall. So when that happens, you actually want to have a more turbulent boundary layer. And the reason why that is because if you have a more turbulent boundary layer, the flow near the wall is faster. And that's what you need to overcome adverse pressure gradient. So the adverse pressure gradient, which is just a pressure gradient, which is pushing back on the flow upstream, that decelerates the flow near the wall. Once you decelerate to the point where the flow is now moving in opposite direction, it has to separate because there's nowhere to go. It has to just go straight up. So if you want to delay stall, you have to have the flow as fast as possible to be able to travel further downstream against this pressure gradient, trying to push it backwards before it finally reverses in direction and has to go up. So in this particular case, if you have a wall which is hotter and it's heating the flow, you're actually exacerbating this problem, which means that you're keeping the flow more laminar when you should be keeping it turbulent because you want to have the flow faster near the wall. If you have it slower near the wall, it means that the angle of attack at which the flow would separate will be lower because that's where the flow can no longer resist the adverse pressure gradient. Now, this also applies to bluff bodies. So, for example, if you take a cylinder or a sphere, whatever you want, and the flow is going over this surface, it's going to experience adverse pressure gradients as well. And you want to have the flow as energetic as possible to be able to delay that point. If you have it laminar, it's going to separate much sooner, further upstream. And so that means that you want to have a cooler wall instead of a hotter wall, because a cooler wall will reduce the viscous effects. It will mean that the flow will transition to turbulence much sooner, and then you can resist this pressure gradient and travel further downstream, and that will then reduce the pressure drag. The reason why it reduces pressure drag is because the wake becomes smaller, because the flow is attached longer. As a result, the friction drag will increase, but because in these flows, the friction drag dominates the total drag, it's actually going to result in a lower drag overall. So in this particular case, you know how we saw that the friction drag made up 75% of the total drag for this wing compared to the pressure drag. The reverse will be true when you have a bluff body or a wing at much higher angles of attack. Okay, so I think I covered that pretty well there. Now let's move on to the final conclusion. Conclusion number 4. Wall cooling control can advance the transition, reduce the transition Reynolds number of the wing section, and increase the friction drag. The lower the wall temperature means lower transition Reynolds numbers, and the higher the drag. So that's in this paper. Make sure to like and subscribe. And if you want to get better at CFD or at theory, as we've been going through here, if you want to get better even more at the theory, check out our courses. We have them in the link description. And I promise, if you think these are great, you're going to be mind blown by our courses. We go through way more in detail and talk about lots of different aspects, a lot more than what we talk about here. So links in the description, and make sure to check them out and tell your friends as well, because they want to get better at aerodynamics. And see you next podcast. Peace out, amigos.